Okay, now we have the sulfurous acid, which is H2SO3, and it deprotonates twice. So we could write it like this, and we have 2H3O plus, and then SO3 2 minus. But if we did that, we're going to lose some information and then make the math really tough for ourselves. As far as losing information, what's the concentration of the hydrogen sulfite or bisulfite ion? That's definitely present in this system, but it's not here. It's because we've taken two monoprotic dissociations and combined them into one, which is fine normally, but here we want to see everything. So we're going to break this up into 2 steps. Then we're going to do a triprotic acid where we're going to break it up into 3 steps, 3 dissociations. So there's 2 dissociations here of the acids, of 2 different acids. So that's why we have 2 Ks. So let's do the first step, H2SO3 plus water. And it's going to become H3O plus and HSO3 minus. That's the first step. Now the second step is going to be the HSO3 minus plus water goes to H3O plus and SO3 2 minus. Get the aqueous in here. This has a Ka1, this is Ka2, or this one corresponds to Ka2. So we do it as this diprotic acid. We're going to treat it as if it's a monoprotic acid, and then when we create this conjugate base of the acid, which itself is an acid because it has an H+, we're going to then send it on to this step to go on to the last deprotonation, or last ionization. Okay, so we have ICE as normal. We have 5 molar H2SO3, 0, 0, minus X, plus X, plus X, 5 minus X, X, and X. So it's just a regular type of problem we've done before. So we then have our X squared over 5 minus X is equal to Ka1. So the concentration of H3O plus times the concentration of this HSO3 minus on top, each of them is X, and then we have 5 minus X over here. And this is equal to 0.013. Now, if the approximation holds, then we can get rid of that X and it'll make our lives easier. I got to tell you, as far as my course goes and as far as my exams, the approximation will always hold for polyprotic acid problems because you already have enough to deal with as far as I'm concerned. But be careful, you want to check anyway, just in case. So here's the approximation. I think I did this, yeah, so this comes up to be 384, which is greater than 100, so the approximation holds. We can get rid of that X. If we solve for X here, we will find that the X, which is the concentration of H3O plus, and also the concentration of HSO3 minus, is equal to 0.255 molar. Double check that, yep. Now, if that was the end of that it was just one deprotonation that would happen, one H plus leaving, then we'd be done here. We'd change this to pH and we're done. But now this guy then goes on to dissociate one more time. So we put 0.255. Now here's the difference. H3O plus has already been created over here. So we have to put that in. That's in solution, so it has to go into our equation. We can't ignore it. I should say one more thing here, that the concentration of HSO3 at equilibrium is going to be 5 minus 0.255 molar, and so that's going to be 4.75 molar. So this one is definitely done. We're done with that acid, and it's asking for all concentrations, so that's the first one that we're done with. Minus X, plus X, plus X. So you can see that we're not done with this concentration or the H3O plus because we're taking some away here and we're adding some to the H3O plus here. So these, we can't count on this being the result because we're going to be losing some here. So this number at the bottom here is going to be less than 0.255. And then for H3O plus, it's going to be greater. We want to remember that because of something that's going to come up down the line here. But let's just continue. So that's why we can't just circle these and say these are done, because they're changing in the next step. So we take the concentration of the SO3 2 minus times the concentration of the H3O plus. I switched them around for a reason. Normally the H3O plus would be on the left side. Doesn't matter because they're just being multiplied together. I'm doing that because we're going to have to do some canceling. And that's equal to Ka2, and Ka2 is 5.62 times 10 to the minus 8. Now we can do this out, but you can see that 0.255 is going to be then divided by 5.62 times 10 to the minus 8 to test for the approximation. That's about 10 to the minus 1 divided by 10 to the minus 8, so absolutely it's going to hold, but let's just check. 0.255 divided by 5.62 times 10 to the minus 8 is equal to 4.54 times 10 to the 6th, which is going to be greater than 100, so the approximation will hold. Now, that approximation holds for either concentration. We're not used to that. We're used to only having one, but it's just math here. It's not anything as far as the physics or the chemistry here. It's just saying that according to the math, if either of these numbers divided by Ka, so if this number divided by Ka2 is greater than 100, then we can ignore this x. And now these numbers are the same, so we don't have to do two tests. But if you had two different numbers here, you'd do the same test on each of them. If each of them was greater than 100, you could delete the x next to it. You say, well, we're adding an x here. It doesn't matter. It's going to be so small that when we add them up, we're going to end up rounding back to 0.255. The approximation should hold in either case. So if you do the test on either of these concentrations, if it holds, then you can get rid of the x next to it. Now look, since these are the same number, those cancel. So a nice little thing happens here. This concentration, which is the concentration of SO3 2 minus, is 5.62 times 10 to the minus 8 molar. Now it's not the concentration of the H3O plus like it normally is, because the H3O plus already has the 0.255 here. So the concentration of hydrogen ion is 0.255 plus x, or 5.62 times 10 to the minus 8. So let me see if this calculator, my computer will even deal with it. Let's see, 0.25, add a bunch of zeros here, plus 5.62 times 10 to the minus 8. Should be, yeah, even it won't even register it. It just rounds it back up. But you can see this is down to the 10 to the minus 8. It's going to, let's try it here. It would equal 0. It says 4, 5, 6, 7. That's what it would equal. And so you can see that's just going to round back to 0.255. So even though we've added some H3O plus to what we had from the first step, it's the first step that decides the concentration of H3O plus. So H3O plus is decided in the first step. That can save you some time, especially if it's a triprotic acid, because that applies for the triprotic acid as well. So the concentration of H3O plus, see, I'm running out of room here, H3O plus equals the concentration of HSO3 minus, which is 0.255 molar. The HSO3 minus also lost some of its concentration, but it was so little that it rounds back. So we have got this here. So we have all the concentrations now. We have this one up here for the original acid, these guys here, and then the pH is going to be the negative log of 0.255, which could have been found in the first step. So I think I have it down here, and this is 0.593. So we have all the concentrations, I think, there, and the pH as well. Okay. Now, the triprotic acid, same kind of thing, except we have 3 steps. I'm going to work this a little bit faster. And so we have H3ASO4, and you're free to use H3A if you want, the general form, but I'm going to just draw these guys out so that I can point directly at the concentration. Since it's asking for all the concentrations, we got to make sure we put them all in here. And then we have H2ASO4 minus ICE, 6 molar, 0, 0, minus X, plus X, plus X, 6.0 minus X, X, and X. I can even put it over here, X squared, 6.02, 6, I was doing Avogadro's number there for a second, 6 minus X is equal to 5.0 times 10 to the minus 3. The approximation does hold. It turns out to be the when we do the ratio, we find that it's about 1200. So the approximation does hold. And X, which is the concentration of H3O plus, and you're free to try that. You should try the approximation just in case I do something on the exam that's a little bit different. But we can pretty much tell that it should hold. Looking at this is 6 times 10 to the well, it's almost 10 to the 1, and then divided by 10 to the minus 3, so it should hold. Here's our concentrations. Now, the first thing is this is the correct answer for each of these. We're going to add a new amount to H3O plus in the second and third steps, and we're going to take away something in the second step from this, but that's it. They're going to round back. And now this 6, now the concentration of H2O is going to be 6 minus 0.173. So this is 5.83 molar. So we already have 3 of the concentrations that we're going to need. And the pH can also be determined from the first step. So might as well do it now. So we have, negative log 10.173 and, oh yeah, there it is, 0.762. I can guarantee you, and you can double check if you're in doubt as you go along, that these concentration H3O plus is not going to change enough. It's going to round back to this number as we go through the next 2 steps. So the pH can be determined in the first step. This will save you some time. If I ask for the pH, just the pH of a triprotic acid system, you can figure it out in the first step. So I might do that depending on how much I've given you for other problems. If I look at it and say, oh man, this would be a 3-hour exam if I made them do all this stuff out, and I might give you a break like that, but you have to recognize that I'm doing that. Otherwise, it doesn't hurt you if you have to go through, all it does is waste your time if you have to go through it and say, oh geez, that's right, pH can be determined in the first step. I didn't need to do all 3 steps. You don't want to do that. So you can see here that we're setting ourselves up for that nice little play that we can make when the approximation holds. I'm going to put this over here. We have 0.173 plus X times X over 0.173 minus X is equal to Ka2. Ka2 is 9.33 times 10 to the minus 8. Now, this is about 10 to the minus 1 divided by 10 to the minus 8. So that's going to be 10 to the 7th. Or somewhere around there. Whatever it is, it's way, way above 100. So on the exam, you might want to note that, at least in passing, a real quick calculation. But here I'm going to just keep going because we've done this before on the previous problem. Note these concentrations are the same. So X, which is the concentration of ASO4 minus, is equal to 9.33 times 10 to the minus 8. That's Ka, and just make sure you put the units of measure in. Always units of measure. Haven't talked about that in a while, but make sure you put those in. Now the x, notice this is 10 to the minus 8. If you try it, you can add these on. Your calculator might not even register it. If you want to do it by hand, you'll find that the 9.33 is way down the line, and you're going to end up rounding because you only get 3 significant figures for your answer. Now, because it's a triprotic acid, we have one more to go. We have HASO4, whoops, go back up here, this is 2 minus. That didn't really change anything, didn't change anything at all, but it's good to have the right charge in there. And this is going to have a Ka, that's the Ka3 up here. And notice, one thing you should recognize is that the Ka2 is less than Ka1, always. That's always the case. And then Ka3 is going to be less than Ka2. So it's always going to be Ka1 is greater than Ka2, which is going to be greater than Ka3, and so on. If there were 4 hydrogens that could deprotonate, you'd have Ka4 would be down here. And there's no limit to it, but normally we only do 3. Because that gets the point across. But if you had 4 or 5 or 6, you just keep going along this line. Now, the concentration of HASO4 2 minus, these guys here, is 9.33 times 10 to the minus 8 molar. We don't have any of this yet, but we do have the H3O plus. We've been carrying it through 2 steps now. So what about that x again? You know, if you that doesn't get carried through because it rounds back to that, and this is minus x plus x plus x, 9.33 times 10 to the minus 8, and then 0.173 plus x x. Now this looks like it's going to be kind of messy. Let's write it out. Now let me write it as it's written here. We put in the concentration of H3O plus times x. I'm not sure why I put parentheses around that. Not the end of the world, but it doesn't help us. 0.93 times 10 to the minus 8 minus x is equal to Ka3, which is 2.95 times 10 to the minus 12. And now 0.173 divided by this number is going to be in the billions, so the approximation is going to hold for this guy. Now this one is not as clear cut. I mean, I see it, but you might not see it yet, that is still going to be greater than 100. So we're going to take this concentration divided by this Ka. If it holds, then we can get rid of that x. If not, then we have to solve it. We can solve it still, it's just trickier. And let me make sure I have everything in there right. So we have 31,627, so definitely this can go. Now it's easy because it's just 2 numbers, and so we solve for it. And I'm just working this out by the computer, the program. And x, which is the concentration of ASO4 3 minus, is equal to 1.59 times 10 to the minus 18. I think that's an 18, yep. Molar. Hardly matters when you get down to that point, but we want to get it right. But notice that if we have, that's our last concentration. We've figured out all the concentrations, we've figured out the pH. This last concentration is equal to x as well, but if we add this number onto 0.173, of course it vanishes, because this 1 is going to appear 15 places down the line. Now here it's 9.33 times 10 to the minus 8. We add this on, with still the first time we're going to come across a non-zero number is 10 places down the line, or something along that line. So definitely the x, this concentration does not affect either of these guys, and so we're done.